All right, how's everybody doing today? Today I want to do something a little bit different. I know that a lot of times when I'm showing some books, there's some higher level mathematics in it, and people get intimidated by it. But I wanted to take some time today and just show you something that's really unintimidating. Show you some calculus that's actually fairly simple, so you can get an idea of what it's all about, and also just see that not all of it is that intimidating. Not all of it is that difficult. So, granted, this is an easier problem, but and it's easy. It's not even that the problem's easy, but we're going to use a technique that's pretty easy to solve this problem. So, this is a limit. Now, what is a limit? A limit is basically just showing you a point that exists on a certain graph. So if we were going to graph this limit, again, this is not going to be exactly what it is, but if I'm just wanting to show the idea, let's say, remember in calculus, we're dealing with rates of change, right? So in all the previous forms of math, what we used to do is we would worry about lines and such that were just basically straight. Now we're going to deal with lines that are curved, that have a rate of change in them. Okay, like that. Now, what our limit's going to be, basically, our limit's just going to show us a relationship at 2 points that converge on that line. Okay, so let's say it was there. That point there would be our limit. Okay? So, this is a typical expression in which you'll find a limit. Problems with limits are usually expressed in some kind of polynomial, which is what we have here. So this is a polynomial expression. It's just a polynomial expression that's being divided. So that's what you see on top. And on bottom we have a polynomial. And then on the left side, we have the condition of our limit. So that says we use LIM for limit. So that says limit as x approaches 1. Okay? What's the limit as x approaches 1 is the idea here. Now, again, as I said earlier, there's actually a couple different ways that we can solve this. I'm going to show you the easiest and most simple way, because again, the point of this is to show that, calculus isn't always that difficult. So there's techniques that you develop and get to learn that'll show you how to solve things simply. Before I get into that, I want to mention that there's about 3 different ways that you could do this. And in a calculus class, you will learn these 3 different ways. The first way, you're going to learn basically the longest and most difficult way, which is that would be to use the formula of the tangent line. Okay? That, I probably wouldn't do it on a video on this channel, but on my other channel, at the symposium, I'm actually starting a math and STEM channel for that. And I'll go into more detail on things that are more technical on that channel. But here again, just an overview. So one way you're going to do this is with the tangent formula, okay, which is pretty long. And then there's another way you can do it, which is algebraically we could do it. Which algebraically, what do I mean by that? I mean just like you might have done in algebra before, where you would get the denominator the same. So what's on the bottom here, that would be our denominator, and you would get that the same on top and bottom, and do your algebra there. It's kind of again a long-handed way to do it. What we're going to do here is we're going to use something called L'Hopital's technique here. L'Hopital's technique actually makes this really simple for us, because all we have to do is find the derivative of the top and bottom until we can actually solve the problem. So one thing I haven't mentioned yet is the essence of our limit, the way we figure out limits, the first question we have to ask about a limit is if it exists or not. We want to see if that point, like I wrote earlier, if that point exists on that curve. One of the ways to figure this out or see if this is even doable is to plug in your value for x on the bottom and see what you get. Okay, so we have to see what we get first. We can check the limit. Typically, you can always guess that if you're given a limit problem, especially in a course, that it's not going to solve, because then there would be almost no point in doing it, right? Because if this gives you any number other than 0, then it's possible to do the limit exists, and it's possible to just solve this really easy. All you have to do is plug in x, and you basically just do the math, and it's there, right? It's more like arithmetic. So if you're given this problem, you're going to know most likely that the limit doesn't exist, but we can check that. We can check if the limit exists. All we have to do here is write in (1 to the third minus 4, 1 plus 3. Again, why are we using 1? Because that's our limit as x approaches 1. So if we do 1 to the third, we still get 1. If we do 4 times 1, we get 4. And if we do plus 3 here, so order of operations, right? We can even talk about that. So we go add and subtract from left to right. So we're going to get here -3 plus 3, -3 plus 3 is 0. Bam. Again, not a surprise if we're given a problem like this. That's what it's going to be. I actually got this problem from a Facebook page that I follow. That's a calculus Facebook page, and I thought, oh, this will be fun to do because it's simple, and it might be a good way to introduce to some calculus to people. So here we are. So we have a 0 here, so we know that we can't just solve the limit as it's laid out here. We have to do something else. Okay. Again, there's an algebraic way to do it, and then we also have the equation or the formula for the tangent line to do it. All of which, again, would take much longer than what we're going to do here. So just erase this. We know that our denominator comes out to 0. So what do we do with L'Hopital's rule? Well, L'Hopital's rule basically states that all we have to do is find dy dx, or we can say f prime, or however you're used to talking about derivatives. So we can find the derivative of the top and bottom. And finding the derivative in a problem like this is fairly simple, because all we have to do is use the power rule. Again, if you aren't familiar with derivatives, well, you can get familiar with them now. All we're going to do here, and it's customary, I have to say, let's keep with the custom. It's customary to every time you do this, before you actually solve this. So what's going to happen is basically we're trying to get the denominator to equal something other than 0. And then once we do that, we can plug in our limit, which is in this case 1, and then we can just solve for it like arithmetic, and it just works out and we get an answer. Okay? But until we get to that point, we have to keep the limit with our problem. Right? Because that designates that we're just not there yet. We're not ready to plug in the actual number into our equation. So we're going to put the limit there, and then we're going to find the derivative of the top and bottom. So can we find that? Yes. So what's the derivative? How are we going to find the derivative? Well, again, the derivative of power is very simple. All we do is we subtract 1. Well, let's say this. First we do, so to find dy dx, we're going to we're going to move the variable into the constant. So this is going to be our variable, which is here annotated as n. So we have x to the n power. We're going to turn that into a constant, which means we're going to put it in front. So we're going to take it from there and put it there. And then we're going to decrease the number that we had by 1. So I can put the n here, minus 1. Okay? And that's the power rule for the derivative. Okay? Okay, so that's all we do, is we take the exponent, we bring it forward, and now keep in mind that if there was another constant here, like let's say it was 2, then you'd multiply by that constant. So you multiply by the constant that's already there to get your new constant number, and then you reduce the exponent by 1, and then that's your derivative. And we do that to every single expression within this problem here. So for 3x, what's the derivative going to be of 3x? Or x to the third. So the derivative of x to the third is going to be 3x. It's going to be 3x because we bring the 3 in front and multiply. So we're doing 1 times 3 is basically what we're doing. X to the, it's not x to the third anymore. We have the minus 1, so it's going to be x to the second. Okay? So that's going to be x to the second. See if I can see my board here. And then minus, now we have 3x squared. So we have to multiply the constant by our exponent, which is 3 times 2, which is going to give us 6x. Now we drop 1 from the exponent, so we're just going to have a 1. I don't have to write it there. That's just implied, okay? And then for our x, we do the same thing. So you can just kind of remember it because there's an imaginary 1 here, right? There's an imaginary 1. So if you multiply that 1 by the imaginary 1 here, you just get 1, right? So if you just have a variable, the derivative of a variable is just going to be 1. And then the derivative of a constant is always 0. So the last number just disappears. Okay, so that 1 just disappears. Now we do the same thing on the bottom. In this case, we have the same derivative that we had on top, so it's just going to be 3x to the second minus, what do we have here? We have an imaginary 1 here, so we're just going to have that 4. And remember, if we have that imaginary 1, that means 1 minus 1 here. So we're just going to have 4 for this, and again, our constant disappears. So that's L'Hopital's rule. Now the thing about L'Hopital's rule, which is why it's so convenient in a certain way. So let's say we did L'Hopital's rule. That means we basically found the first derivative. Okay. So this is the first. This is the first derivative. But let's say this didn't work. I'm going to give it away already here because we're just doing this for practice. That's going to work. So we only had to find the first derivative. Sometimes you have to, if it doesn't work, what do? This is why L'Hopital's rule is so convenient, is because if it doesn't work, you just do the derivative again. You just take the second derivative. So you take this and you just do another derivative. You take the second derivative of the derivative, and then you see that if that works. If that doesn't work, you just take a third derivative, okay? And if that doesn't work, you take another one. So you just keep taking the derivative until what you have on the bottom comes out to something other than 0. So in this case, if we take 3 and we replace x with 1 to the second minus 4, then what we get here, 1 squared is going to be 1, so this is going to be 3 minus 4. 3 minus 4 is going to give us negative 1. So we have a number now that's other than 0. So we can now this tells us that now we can actually find the limit. So we don't have to put our limit symbol here. We're actually going to plug in. This is where it gets simple. All we're going to do is plug in our x value for the rest of the problem and just do the math, and then it's over. Okay? Like I said, pretty simple stuff here. You see, if you're in a calculus class to get to this point, yeah, you have to do some struggling, right? You got to learn the other ways. But after that, you find that some of these limits are going to be very simple for you to solve. So now we're just doing basic, you know, I don't know if I even call it algebra, just like arithmetic, right? So we have on the top, we know that this is going to be what? We did that over there, right? So we're just going to have 3 minus -6 times 1 is just going to give us -6 again, and then plus 1, so that's our top. And then on the bottom, we're going to get 3 again here, minus 4. So we already knew 3 minus 4, we did that over there, is going to be -1. On the top, we're going to get 3 minus 6. 3 minus 6 is going to be -3 plus 1. -3 plus 1 is going to give us -2, so we're going to subtract, take the sign of a larger number, and then we have -2 over -1, which is going to give us +2, and that's our limit. What does that tell us? Is that that there is a limit that exists at the value of 2 if we graph that figure. Okay. Again, just wanted to share that with you guys. As you can see, something like that, not that intimidating. If you're interested in more math videos, let me know. Again, I'm going to be starting and doing some more math videos at the symposium, the STEM edition of that that's at the symposium. Other than that, we'll keep it going with Stan Gibilisco and the Learning Electronics series. I'm going to be posting a video about that soon. We're going to keep going with diodes, actually. Okay, so I'll see you guys soon. Have a good one.